Welcome to May 17th's LeetCode Challenge. Find a corresponding node of a binary tree and a clone of that tree. Given two binary trees, original and cloned, and given a reference node target in the original tree, the cloned tree is a copy of the original tree. Return a reference to the same node in the cloned tree. Note that you are not allowed to change any of the two trees or the target node, and the answer must be a reference to a node in the cloned tree. So for example, we have the original and the cloned, and we've given a reference to the target node 3 here. And you want to return basically the corresponding node of the binary tree in the clone tree, which is number 3 on this side right here. So basically, return 3, and all the examples, original and the clone trees are shown. So the target node is yellow as the green from the original tree, and the target node is yellow. So the answer is the yellow node right here. If there's one node in each, if the original node, target node is the same as the original, therefore return the cloned, F7. Similarly, we have basically a symmetrical tree or a linear tree, where we have everything being on the right node. If this points to target of 4 on this original tree, then the clone will also be 4 as well. Our constraints that the number of nodes in the tree range between 1 to 10 to the 4. The value of the nodes is the tree are unique, so that's good. And the target node is a node from the original and it's not null. Sorry. Okay, so let's repeat values of the tree, the same on the tree aloud. I'm not sure about this, but let's go about this. So this is a binary tree. So one of the things you want to define is how we're going to go through the entire tree. So we could use a depth first search. And I'm going to use the recursive in-order traversal. So basically, a depth first search in-order traversal will be able to utilize a recursive function in order to be able to in-order traverse a tree. That's so to keep it simple, basically we go to left node, right node, left node, node, right node. Basically, that's what we're going to do in that direction. And we're going to do a recursive call to the left node, and then do all the business in that order, in that node. And similarly, we're going to check to see if its target node is equal to the target node. And then we do the same thing, recursively call the right node. That's what we're going to do. So in order to do that, let's develop a in-order traversal function. So let's do that. We're going to do in-order, and we'll call that function. It's going to take in the original, and that's going to be a tree node. And then we're going to take in the clone tree as well, and that's going to be tree node. Just some documentation there, tree node. And it's actually going to return a value, so int, I believe. Yes, because that's what we want to. Nope, it's going to return a tree node copy. So in order to do this, if the original exists, what we're going to do is do a recursive call to in order, and we're going to take in the original dot left and copy dot left, and recursively go through that. If the original is target, then we're going to update our self dot output to be our clone node. And then we just recursively call the same thing in order, and we're going to do the same thing to the right side. So original dot right, take in clone dot right. And then we do the same thing, exit this loop. We do in order, taking the original. We call actually the function in order, taking the original and the cloned. And then we want to basically exit this actually, because we're in the definition, call the function in order, passing the original and clone, return self dot output. Alright, let's see if this works. Let's see. Oh, what am I doing? Sorry, function. Just do that, and then this can go back. This can go back. This can go back. Alright, seems good. Excuse me. So basically, the time. Oh, accepted. Awesome. So the run time complexity of this is big O of n, because we have, since this one has to visit each node, so therefore the n number of nodes in the tree. Space complexity, or the runtime memory usage, is also big O of n, because if we have a degenerative tree, then we know that the shape is like a linked list, such as this case here. Therefore, the maximum runtime stack is the deepest node. Therefore, being, for instance, if you have this last node right here, then that's going to be the being processed. If it's a balanced tree, however, as none of these actually, then we know that if the space complexity will also be closer to big O log n times. So the worst case scenario will be big O of n, being this degenerative tree example here. If we were to take the last node, it would be n node values, n node memory. Alright, that is all using a depth first search in order recursive traversal. Alright, have a great day, guys.